All right, everyone. So let's get started. Okay. So today we are going to talk about amplitude splitting interferometers. There's a few different varieties of these that I'll go over. I don't think I'll have time to get to multiple beam interference, so you might see a little short video on that next week, posted as an addendum to this lecture. Okay. Oh, before I go on, I realized that I never talked about test one in the class, and I apologize for that oversight. I did send out an announcement about it, which is that everybody did really well. I guess that's why I wasn't so worried. Everybody was like doing so well on the test. I was like, wow, everybody gets what I'm talking about, which is good feeling. But so I think the average was like over 60 out of 70, which is very high. And I think I saw like maybe one question that was perhaps an issue. And that was actually not even on the main test, but more on the yeah, okay, so okay, here. So there were 5 questions in the multiple choice, and I think for some reason it was question 1. This one that gave people a lot of trouble, or at least it had fewer people get it right than the other questions. All the others were well over 70%, but this one was like 60. So I just wanted to go over it in case anybody still is confused about it. So you have an electric field vector with a expression cosine 10z minus whatever z, and x hat is just a unit vector, direction of x. All the numerical values are in SI units. What is the velocity of the wave? Again, assume SI units here, so it's fine to just write a number down. So meter per second is SI unit. So the question here was 10z minus. So you want to express this cosine kz minus omega t, you could write it as kz minus omega t. And then from that, you could get 2 pi over lambda equals 10. And 2 pi times the frequency equals 20 times 10 to the 8. From that, you can solve for f times lambda. So that's one way to do it. And you will then get the answer 2 times 10 to the 8. Another way to do it is to sort of recognize that all waves fall into the general function of which form of a wave, which is f, where f is any function of z minus vt, where v is the velocity. And so this is almost in that form. It's z minus something t, but there is a factor 10 in front of z. So you pull that factor 10 out, and you get z minus 2 times 10 to the 8. Okay, so that's the other way to know that that's also the right answer. So both approaches will give you the right answer. So I just wanted to make sure everybody follows it. And all the other questions people had no trouble with, so I don't think I need to go over them unless somebody has a question for one of the other problems. Yeah, I think everyone got these other 2 problems: the Snell's law problem. I'm sorry, the aberration. Most people got
so for problem 1, so for intensity we just compare the square of the intensity. Problem 1.
This one you mean? Oh, for everyone would have seen a different set of which order that is in, because it's just the way the grade scope works, it randomizes the questions. But yes, you must be referring to this problem.
Yes,
the one with the different. Yes, this goes as a square of the mirror diameter. We talked about this. I actually introduced this problem in class, so yeah, we talked about it. There may be some. I don't know if anybody was confused about one of these. So everybody understand what I'm saying, which is that for a lens, we know that the brightness goes as d over f squared, and in the absence of that, extra information, you can just treat the focal lengths as roughly equal or not differing by a whole lot, and that is true. They just because of the geometry of satellites, they kind of keep all these things roughly equal. So then, when the mirror diameter has increased, the intensity or the brightness of the image increases as the square of the diameter. And that's something that I talked about in the
Yeah,
class.
when I'm doing this problem, so I'm trying to argue. I know it's squared, but I'm arguing is the number of the density of photons. The density of photons is uniform, and then this is how many photons is collected.
Yeah,
in the
yeah, it's roughly that idea.
And then the number of photons is proportional to the intensity. And then how do we argue this? When I was doing the problem, I was trying to argue or trying to figure out from the number of photons, and then how does this give rise to the intensity?
The number of photons is proportional to intensity. Because the intensity is just watts per second per unit area.
Oh yes.
So if you convert watts to number of photons, it's just the joule per second, and one photon has energy h nu.
Yeah.
And therefore it's just number of photons times energy of one photon gives you the per second.
This can be done.
Per area gives you the number of photons.
Yeah, this can be done. This can be done using the dimensional analysis.
Yeah. Yeah, I think in the class when I talked about it, I also used some kind of variety of dimensional.
But you didn't go through that.
No, I did. In class. Yeah, we talked about image brightness in class.
Oh, yeah. I was aware of that, and then I was trying to understand from the number of photons,
There's a derivation. So if you go back to lecture, maybe 1 or 2 lectures before the exam, I derived the difference between depth of field, how depth of field varies, and how image brightness varies based on the geometrical consideration. But which of course can also be argued based on the number of photons.
Yeah.
Okay. So it's just basically the solid angle captured by the mirror. So solid angle goes as the ratio of the diameter. Okay, so I will, if nobody has any questions about the test other than that, we'll go back. Some reason. This desktop. Okay. No. Again. Okay, so that's about test 1. And as I said, if you have any questions, I'm available after class, or I can set up a meeting with you if you have concerns about your test or something. If you go to the course modules under the course, then I posted the solutions to the course to the test. So if you have questions about what if you got one of the problems slightly wrong in the test, then you should be able to look at the solutions and see where you might have gone wrong. And of course, if you have questions about how we graded something, like for example, you don't agree with the grading, yes, please email me and we can set up a time to talk about the grading. Okay. All right. So that's about test 1. Okay. So now I'm moving on to talk about the amplitude splitting interferometers. So in amplitude splitting interferometers, in Young's double slit, we took one wavefront and then we took pieces of it, 2 parts of it using 2 slits. So that's a wavefront splitting interferometer. And then I showed you other examples, which are all based off of that. But now we're going to take the same wavefront and we're going to split it into 2 by essentially reflecting and transmitting a part of the same wavefront at some interface between 2 dielectrics or metals, etc. And we're going to recombine them at a detector or a screen. Okay. Again, the same principle of path length difference has to be less than the coherence length for interference to occur. It still holds. That's a general consideration. It's just the way in which we create the beams for interference is different. Okay. So examples of this are all around us in nature. So like, for example, the colored fringes from which you might have noticed in like soap films. If you have an oil slick on the surface of the road, you might see like bright colors from it. If you look in a sharp plate glass window, you might see like colors and windows in your house, etc. Just some pictures of like soap film interference fringes that you might see in different such dielectric films. Okay. And one of the big technological applications of our understanding of interference and dielectric films and so on has been through the thin film coating technology that was developed in the 1930s and then afterwards military applications in World War II. This is essentially through the development of like vacuum, ultra high vacuum technology and radio frequency sources of like various materials. It is now extensively used for mirrors and lasers and so on now. So this is a very important application, technological application of this thin film interference, which I'll talk about later. So before we go on, we should talk about the two major types of fringes that are observed in all of these situations. One is called the fringes of equal inclination or Haidinger fringes, and the other is called fringes of equal thickness or Fizeau fringes. Okay, and I'll talk about them when we discuss those sections. So first, let's discuss fringes of equal inclination. So what this comes from is that you have a thin film, let's say a soap film or oil on top of water, etc. And this has a beam that comes in. This is a wave, and you get one reflection from the top surface of the material, and then a second reflection from the bottom surface because there's a refractive index difference. Again, here, so the two of them recombine, and because of the thickness of the film, there are extra waves. That's what this is supposed to represent, that this wave undergoes slightly more waves inside the material. And you can almost see now the intuitive picture for this is how many wavelengths will fit inside in this piece of film will decide whether you get constructive or destructive interference. So for example, if there's a total integer number of wavelengths that fit inside the film, then you get constructive interference. And if you get, in principle, but we'll talk about a couple of different subtleties that change that, okay? We'll talk about that in a minute, okay? And we are going to, and of course, if you get a half integer number of wavelengths inside, then you get destructive interference, except for two subtleties that I'll discuss in a minute. Hopefully that's clear to everyone, right? That if you get integer number of wavelengths in here, you should get constructive. And if you get half integer, you should get destructive interference. So in our first pass through this problem, we're going to assume that there are only two reflections, and we're going to assume both are roughly equal intensity. Now you can already see that why this is an approximation. Well, we know from Fresnel coefficients that when a beam reflects off of a dielectric interface, we don't get necessarily the same intensity from the two beams reflecting here as we would from a single beam. Okay, so these two may not have exactly the same amplitude when they come back and interfere. Okay, that's one problem. The other problem is that we have assumed only two reflections, but there's nothing to stop this beam from reflecting again here and then reflecting again and then coming out again. So that's a multiple beam situation. Okay. So we won't consider that case right away. Okay, we'll consider only the simple case first to understand it. Okay, so and now I talk about the two subtleties that I want to remind you of, and this has to do with phase shifts upon reflection. So back when we were discussing Fresnel coefficients, I showed you that, for example, the S polarized light undergoes a phase shift of pi for external reflection, meaning Ni is less than Nt, meaning the incident refractive index is less than the substrate refractive index. S polarized light undergoes a pi phase shift. P polarized light undergoes 0 phase shift. Okay, let's ignore P polarized for a second. Let's just talk about S polarized. Okay, just for ease of understanding. So when Ni is less than Nt, which means that you have air, then you have a film. Okay, so then the S polarized light undergoes a phase shift of pi. But what matters, of course, is not that phase shift, but the relative phase shift between this beam and this beam. Okay, so that means what phase shift does this undergo here, and what phase shift does it undergo here? And in this case, this is an internal reflection case, because now that we are assuming the film is say like oil on water or soap film in air, etc. This film thickness will be greater than the outside medium over here, which means that this is an internal reflection. So what we need to really understand is we need to compare the phase shift for S polarized light in one case, which is external reflection, and the other case, which is internal reflection. And you can see in the first case, there's a pi phase shift. In the second case, there's a 0 phase shift. So relatively, the two beams will have a pi phase shift. And that's all that matters, the relative phase shift between them. Okay. Similarly, p-polarized light, if I go back one step, p-polarized light has a phase shift of 0, at least for angles less than about the Brewster angle. Okay. And for roughly for about 45 degrees or so, this is for glass, of course, so if this angles change, it has 0 phase shift here. So you see that p-polarized light, has pi phase shift here, p-polarized light. So again, there's an internal and external reflection. The two reflections differ in a phase shift of pi, at least for small viewing angles, roughly 35 degrees or so, which is actually, generally speaking, roughly the angles with which we view most things when we are looking at them because of various effects like the Brewster angle and so on. Okay. So anyway, so the point is, just please remember this, and I'm summarizing it all here. Okay. So, so the first one is, and this is very important. So we must sort of remember this, which is that external and internal reflections are out of phase by 180 degrees, at least for angles, as I said, roughly less than 30 degrees or so. And so let's take two cases. So first case is N1 equals N2 lesser than NF. So there's N1, the medium in which the beam is coming in. NF is the film thickness, film refractive index, and N2 is the material underneath the film. Okay. Usually say N1 equals N2, which is a soap film which is suspended in air. So there's air on both sides. So N1 equals N2, approximately 1. And then there's the film thickness NF. Okay. Or you take a glass slide, like a shop window or something, a piece of glass, which is small in thickness, and then again there's air on both sides of the glass. Okay, so that would be the first case, and in that case, both beams will be out of phase by 180 degrees. The second case is N1 equals N2, but they're greater than NF. Where is this situation going to occur? Any thoughts? So N1 equals N2 equals to NF. This is like an air film which is suspended between two glass slides. Have you seen such a situation in your lab experiment? An air film between two glass slides. Might have remember from your lab experiments a situation that might be true. Remember one of your lab experiments like that? Air film between two glass slides. Anyone? Because N1 is equal to N2, but it's greater than the film in which the interference, the two beams are getting reflected. No? Newton's rings, right? Because the first reflection takes place in the glass of the lens, the second from the optical flap that's underneath. And in between is an air film, right? So that is an example of this situation. Okay, N1 equals N2, it's an air film, it's glass, N1 and N2, and then film is air, which is less than the glass. So N1 equals N2 greater than NF. Again, the two beams will be out of phase by 180 degrees. And then there will be one more situation, which of course is when the film thickness lies in between N1 and N2. And that can be either N1 is greater than NF, greater than N2, or N1 less than NF, lesser than N2. Well, in this case, there is no phase shift. Okay, so this is important to know. Okay, when there is no phase shift. So the phase difference, delta, is equal to K naught times the optical path length difference plus or minus pi. Why do I say optical path length difference rather than just the path length difference? That's because of the fact that we want to take into account these refractive indices carefully. Okay. Let's just talk about that for a second because it's an important concept and we will be using it again and again. Okay. So earlier we've talked about path length, about the phase shift delta. Okay. And we wrote down that this is, in general, it's K1 dot R1 minus K2 dot R2 plus epsilon 1 minus epsilon. This was the most general phase shift for two beam interference. Okay. And in most situations, what we have done is we have said this is approximately some K times R1 minus R2 plus epsilon 1 minus epsilon 2. And we call this, of course, the path length difference. We wrote this K as 2 pi over lambda naught, where lambda naught represents the wavelength of the light in vacuum or air, the air having roughly the same refractive index. Okay, so this is, and then we derived different R1 minus R2s for a double slit. For a Young's double slit, it was like A times sine theta, where theta was the angle. But now we have two beams, okay? So for example, here we have a beam that's reflecting off of this, and then it goes through a medium and reflects again, okay? Right? And this medium has some thickness, has some refractive index NF, and then of course up here is N1 and down here is N2, for example. And typically N1 will be N2, but as I said, there may be situations where it's not. Well, in this case, the two beams that are undergoing reflection or are going interference, one of them is going in a different medium. Okay. Now, what does that do to the wavelength? What happens to the wave when it goes in a different medium with a different refractive index? Does the wavelength remain the same? What about the velocity? Velocity does not remain the same. So then what changes? If the velocity is not the same, does the frequency change of the wave? Or does the wavelength change? I said that I would wake you up in the middle of the night to ask this question at some point. And I'm asking you in bright daylight, so you should know this. Right? See, we didn't take my class. How would you figure this out? Knowing some basic facts about this. You can talk to your neighbors, figure it out. So if I go from a medium like air to glass, I have a wave. Does anything change inside the glass?
Yes, the wavelength. But the wavelengths will change inside the glass.
He thinks wavelength will change.
To lambda over the refraction index.
How many people agree with it? You think wavelength will change or frequency? Why not frequency? We know the velocity changes. Everyone is okay with that, right?
Yes,
Velocity.
the velocity will change.
Hold on. I saw someone put up there. Was it you, Stephanie? Yes. Yeah. What is your question? Oh, you have a comment?
Yeah.
Yeah. Yes. Nice. So the photon energy, or you can argue that if the frequency is if you want to think of a classical picture, you can think in the classical picture that that's what is causing electrons to vibrate. So it doesn't really change when you go from one medium to another. Well, what changes then? Something has to change. So the velocity changes, right? Is the wavelength. Okay. Everyone is now okay with this? Yes. So you want to say something, Robert?
Like also, if the frequency changed, you would have like the boundary conditions wouldn't make any sense.
Yeah, exactly. Exactly. So at any one point, then you couldn't make if the frequencies were different on one side versus the other, you might have problems with like matching up the boundary conditions at all times.
So how do we argue this from the electron atom interaction from the microscopic pictures? So,
yeah, we are assuming in all this that this is elastic scattering that's going on. Yeah, if you of course allow for inelastic scattering, that's how you end up with things like Raman scattering and other types of scattering. But we're not considering that here. Okay, so now we have agreed lambda in the medium or film, etc. Lambda f. Let's call that lambda f. In the film is now not the same as lambda naught, which is in the air. So what's the relationship between lambda f and lambda naught? Since you agreed that it's the wavelength that changes in the medium. What's the relationship? Given that the velocity changes, How does the velocity change? Can anyone tell me that? Velocity in the film for the wave is equal to, how is it related to the refractive index? Hold on, let me see. Somebody. I call on a group. I'm sure you guys know this answer. How is velocity related to the refractive index? Velocity in the film equals velocity of light times the refractive index plus the refractive index. No? Which one is it? Are you raising your hand or just?
Is it divided by?
Exactly. Very good. Thank you. Divided by the refractive. Good. So if the velocity is equal to c over n, this implies since v equals lambda in the film, v film is equal to lambda in the film times the frequency. I'm going to call the frequency as mu, just to avoid using f all the time for that. Okay, so that's the frequency. Sorry, my v and my mu's all look very similar. Okay, hopefully you can tell there. This is the frequency. Okay, so from this you can now show that lambda f equals lambda naught divided by n. Okay, and so all right, coming back to here, we were talking about the interference between a beam. This is beam 1 and beam 2. Well, beam 2 goes through the film. Okay, so the k for this delta is no longer the same. K1R1 minus K2R2 is no longer the same for the second beam. We have to modify k. So k in air is k naught is equal to 2 pi over lambda naught, right? That's in the air above the film. And then in the film, if we call that 2 pi over lambda f, which is in the film, and now substituting this, we get 2 pi over lambda naught times nf, the film, refractive index. Then putting that back here, what we see is that what we'll have to do to this beam is if we call this path length over here something, I don't know, d or something like that, then we are going to have to write down the path length over here as 2 pi over lambda naught times n film times d for one traversal, and then of course twice, we'll make it higher, it'll be twice d, right? So it'll be 2 times nf times d will be this k1 r1 minus k or r2, it'll be minus sign, fine. And then the first part, which is just, you know, if I will tell you about the fact that it's not exactly at 90 degrees or normal incidence in a minute, but you can see that the only difference between these two beams is really this traversal of the film, but with this extra NF thrown in there because of the wavelength being different. Well, NF or N times D is called the optical path length, as we know from Fermat's principle. And so we say that in these interference experiments in general, that the overall phase difference is just 2 pi over lambda naught times the optical path length difference, not just the path difference, but the optical path length difference because of this situation. And this optical path length difference will sometimes denote by a big lambda. Okay, the big lambda representing, or capital lambda Greek letter representing the optical path length difference, which means I have to take the path length difference and multiply it by the film refractive index. So, and for normal incidence, you can see that, right? Nearly normal incidence where the angle is very, very small, equal to almost 90 degrees, equal to almost 0 degrees, then the amount that this beam 2 travels extra is just 2 times d, but I add in this NF to account for the change in the wavelength inside the film. And this is now easy for you to understand that, you know, if you come in at some angle, okay, now it won't be 2 times NFD, but it will involve some factor that involves the angle. We have to take the angle into account, which I will do in the derivation, but this basic, the simplest case, hopefully everybody can understand that. Is there any question on that? The simple case?
The simple
Oh,
case.
sorry, let me just make sure. Is everyone clear on the simple case first for the nearly normal incidence? That the path length difference is 2 pi over lambda naught. I mean, the phase difference is 2 pi over lambda naught to NFD. Okay. And that you should be able to derive, hopefully, even without any complicated geometry, right? It's just twice the distance because you go once through that and then once back to come to. And now to make this a maxima or a minima, what would I do to this phase difference? What would I set it equal to for maximum? Equal to what for maximum? And what for minimum? Anyone tell me that? Yes.
So for maxima for maxima is 2 pi. The 2 pi is 2 pi. It's
2 pi
multiplies. It's m multiplies. No. It's m multiplies. The phase difference is the difference in the difference of the lengths is 2 pi multiplies multiplies lambda, the wavelengths. So since we have
2 pi multiplies wavelength.
Oh, so sorry, no. N multiplies
M multiplies 2.
M.
Okay. So from that we get that lambda will then be a multiple of lambda. I mean, capital lambda will have to be M lambda naught for maximum. Okay. Right. And for minima, it will have to be M plus half. But also, we need to add the phase shifts, plus or minus pi. That's because we have the internal and external reflections, as we have already discussed now several times. And it's okay to choose either plus or minus sign. It doesn't matter. Okay, you can choose plus sign or minus sign. You'll get the same answer. Everyone okay? What I'm talking about? Okay, now you have a question?
Yeah, so I think there's a difference. So this is
Sorry, before. I want to make sure I don't make a mistake. So this lambda equals M lambda naught. That was for not adding the phase shift. As soon as I add in that phase shift, now this inverts. So now maxima will occur at M plus half lambda naught. Minima will occur at M lambda. Okay. Oh, is that clear to everyone? Okay. That's just the fact that we added this plus pi. Okay, yes, what's your question?
Sorry, I will show you the graph after class. So
Okay.
I was trying to understand it.
All right, very good. So that just summarizes all the discussion that I just told you as well. This is this K naught times lambda. Why it comes about is this, and why lambda is this optical path difference and not just geometric path difference. Okay, so all right, so we have a quick derivation here. I'm not going to spend too much time on this. It's basically the geometry of the problem. So we need to, as I have said, examine what is the extra path length over here. Well, you can see the beam 2 travels this extra distance. Now I'm doing it for like general angles, right? Any general angle. We did the simple case on the board. but now we want to take any general angle, theta I, and theta T over here is the transmitted or the refracted angle. And then, of course, this beam over here does travel a little bit extra in the medium one because it travels this extra distance before the other wave can catch up. And from the point CD onwards, they both travel the same path to the eye or the screen or whatever. So what we need to calculate is the path length difference, the optical path length difference, which is NF times AB plus BC minus N1 times AD. Okay, everyone okay with this? Why I've written this down? That's very important to understand why that's written down that way. Only when you understand that, the rest of the derivation will then just be about calculating this A, B, B, C, and AD, which is just geometry. Everyone okay with that first equation or not? Anyone still have a question on that? Okay, great. Okay, so the rest is just geometry, as I said. So we take this first A, B, and BC. They're in this triangle over here with a thickness D, which has an angle theta T. So we can take like half of that and find that that's just equal to the thickness times that cosine theta. Okay, they're just in that hypotenuse over there. And then AD, which is this distance over here, can be written in terms of AC. Okay. Again, that's just because we have to. I'm not drawing with a pen. So there's this angle theta I. Sorry, it's hard to draw. Screen, that's theta I. And so from there, we can relate that this will be theta I as well, and then this will be 90 minus theta I. So AD in this big triangle over here, AD has AC in it. So we can write AD equals AC sine theta I. And then AC, which is this over here, can again be related to the thickness D times tan theta in this triangle over here. The same triangle. If I call this point over here E, then ABE, AE is obviously half of AC, so we can then calculate that's equal to D times tan theta. So AC is equal to 2D times tan theta. Okay. And then we have to relate sine theta I to tan theta to sine theta T, which we know how to do from Snell's law. So substituting for tan theta T, sine theta I in terms of theta T using Snell's law. Okay. So that's just sine theta I equals NF by N1 times sine theta T. So putting all that back together, I get that the overall path length difference, optical path length difference is 2 NFD. So if I didn't have this cosine theta T, this is just that expression that we had earlier for just normal incidence. But because we have an angle, we introduce an extra factor cosine theta T, which we just derived using this geometry. So that's just a geometrical factor and will be close to, say, 1 for most angles close to normal incidence, say within like 0 to 10 degrees or so. Okay, so I now create so that is just the path length difference, lambda. So now remember the phase difference is 2 pi times 2 pi over lambda naught times that path length difference, which is 2 NF D cosine theta T, and then adding the plus or minus pi. Again, as I said, you choose one, let's say plus pi for like for the internal and external reflection situations. Okay, so the bright fringes now are obtained by equating this delta to 2m pi, as we have done before, we did over here. So now we'll get d cosine theta equals 2m plus 1 lambda over 4. So you'll often see this, when you get bright fringes is because you're some odd multiple of lambda over 4 in reflected light. Okay. And similarly, dark fringes in reflected light will be when we take the case, when we equate that to m plus half lambda over 2. So we'll get 2m lambda over 4, which is, again, just what you would expect. Okay. But again, this is inverted from what you would have gotten if you didn't have that phase shift. The phase shift makes it like this. Okay. Okay, the last thing I want to say about these fringes of equal inclination is that so far we've been talking about it as though there are just two beams that are coming, but in most experimental or real life situations, the fringes would only appear in a small portion of the film from a point source. Why is that? We can see that here in this drawing, okay? So we have, say, a mercury lamp or something which has reasonably long coherence length, and we create a pinhole, just like we did for Young's double slit, and we illuminate the film. Well, I mean, hopefully you can see it from the drawing, but basically some angles of this film will not make it into your eye, okay? Because basically these rays from this will go here, rays at some other angle will go here, and only in a small region, which is where the rays from that point source will make it into your eye, is where you'll see the interference. But of course, most of the sources that we have in nature and so on are extended sources. And so for extended sources, there's always some point that satisfies that angle that we want. So for example, if P1 and P2 are 2 points which are at the same angle relative to the film, so this angle is say theta I, so this source point over here has the right angle to reach P2. Similarly, another point source over here has the right angle to reach P2, and these angles are equal to each other, okay? So that means that this P2 is an angle of, has an interference fringe. That's why we call this fringe of equal inclination, because it's the same angle, okay? And similarly, P1 would have a slightly different angle, but it would also correspond to 2 points, let's say over here and here. So it's always possible to find some points that will satisfy this condition. And therefore, you can think of it as, and another way to think of it is that the film, this film here, due to the reflection, if I were to trace these rays back, there would be a point source here and a point source here, which are spaced apart like a Young's double slit by 2d cosine theta t, okay? And so the lens effectively is placing them at infinity, because it's like kind of, not infinity exactly, but far away, basically, these virtual images. And these virtual objects, whichever way you want to think about it. And the angle of the beams then controls the position of the interference, and again gives rise to these fringes. And the fringe will appear everywhere on the film, no matter where I look. As long as I'm within the lens viewing area, which of course the lens viewing area depends on how many rays make it into the lens, the fringe will appear, okay, on the film. So we can see the fringe in a broader area by using an extended source. Finally, because of the fact that there is a limitation, which is the viewing area of the lens itself, there Haidinger created this setup, which is the one that you use in your lab, which is he took a extended source, and now he uses a lens to view the film, but he puts a beam splitter in first. Okay, and the reason for the beam splitter hopefully is clear now, which is basically that the 2 points which earlier might have escaped if you just directly illuminated the film and looked at it with a lens, some of these points might have escaped your viewing, but now we've made them nearly normal incidence. So almost all the rays will basically make it into the film, and you will get circular fringes again, because these are fringes of equal angle, equal inclination. So all that matters is the angle around the central optical axis. So if the angle is the same, then that's d cosine theta is the same for all of those rays, and therefore you'll get either constructive or destructive interference depending on what condition they satisfy. Okay, and that's why we get circular fringes when we look at dielectric film in this configuration like this. Okay, allows us to view the film fringes anywhere. Beam splitter makes a nice number. Okay, I covered all that. Oh, one important thing to understand is, what about the order of the fringe at the center? Because the reason for this, that the order of the fringe is the highest at the center, comes from this condition over here, which is d cosine theta equals 2m lambda over 4. Let's say we're looking at a dark fringe, right? Because that's the simplest one to immediately see here, but it's the same for the bright fringe as well. Okay. Well, you can see for d cosine theta equals 2m lambda over 4. For theta t equal to 0, which is the normal incidence, this is d. Okay. All right. And for theta t, which is not equal to 0, as you go from 0 to 90, cosine theta t decreases. So the left-hand side of this equation decreases as a function of angle, meaning going away from the center. As I go away from the center, the left-hand side decreases, so m has to decrease. So the central fringe has the highest order, and all the fringes extending away from the center will have lower order in this Heidinger fringe. Oh, okay. So I should stop asking questions. Yes, that took us more time than I anticipated. Okay. All right, so that's Heidinger fringes. So I'll quickly cover Fizeau fringes because they're just very similar. Oh, this is being my way off. So, okay. So now instead of making the angle as the important parameter, we want to make the thickness of the film as the important parameter that controls the phase difference and controls the interference. Okay, again, it's the optical thickness rather than just the thickness itself. It's n, the refractive index times the t. Again, same, that principle is still correct. So again, there are many examples. I've already talked about them. And the interference fringes that we are going to map out here are like contour maps of the thickness of the film. So this is one great application of Fizeau fringes, is being able to view very thin films and figure out where they might be thicker or thinner than they would be. And you can do that with extreme precision using interference phenomena. Why is it? I'll explain in the next slide. Okay, so again, the viewing situation for Fizeau fringes is almost identical to the Heidinger fringes. It's just that what changes is down here is the film is no longer a uniform single film of a single thickness over here. And the way to get that, as you've seen in your lab experiments, is you take two slides and you put a little spacer in between them. Even a piece of tape or something is usually enough to make this happen. Because now the fringes are, the plates are basically forming a wedge. Okay, and clearly the thickness is lower here and higher over here. Okay, but everything else in terms of the viewing angle, the viewing situation is the same. And the reason we do that is so that we can cover the largest area of the film possible. Okay, with this situation. Okay. Okay, again, setup views allows us to view a normal incident. Now, the one difference here is because of the phase shifts. Remember, I told you this situation. Here we have a situation where there is a zero path length difference. Okay, right, almost at the edge. But because of the phase shifts, you get a dark fringe over here. Okay, because of the pi phase shift. Okay. And the first bright fringe is then m equal to 0. Okay. So let's go through that. So d equal to x times alpha. That's because if I assume in the small angle approximation, the thickness of the film d is controlled by how far along the slide I walk times the angle alpha. Okay, just it's tangent alpha, but we'll just approximate that itself. And then, of course, from the interference condition, we get that must be equal to m plus half lambda naught. So you can see that for the bright fringe, that's the situation. Therefore, m plus half lambda naught. So the first bright fringe is that when 2nf times d is equal to half times lambda naught. Again, it works out as nf times d is lambda naught by 4. Okay. And then easy enough to understand again that if I make the angle bigger, okay, then the spacing of the fringes is going to decrease, basically. Okay, because as the angle increases, then the thickness over here increases more quickly with the x, and therefore the spacing between the fringes is going to decrease. Okay. And that's shown sort of here. Okay. Furthermore, as we have also seen, the difference in film thickness between adjacent maxima is lambda f/2, meaning if I were to choose one thickness over here, which is corresponding to a bright fringe, and then I walk over here to another one, that's a slightly thicker area of the film. Sorry, my drawing is a little bit hard, but that the thickness of the film increases by lambda f being the wavelength of light in the film divided by 2. If it's air, obviously lambda f is equal to lambda naught. Okay. So that's a nice way in which we can decide whether a film is uniform or not by watching the spacing of these fringes increase or decrease. Like if you're trying to place two things down into contact and not have any wedge between them, we just watch the spacing of the fringes decrease or increase, as the wedge angle reduces. Okay, so that is a nice way to tell, and then we can even determine which areas of the film or the two plates or something are almost exactly touching with each other or the same height or the same thickness with respect to each other. Okay, I am almost out of time. I just wanted to show you some examples of these equal thickness fringes in like a soap film, and these will tend to be straight line fringes, not because it's again governed by the thickness of the film, and the thickness of the film is not governed by the angle relative to the observer. Newton, for example, discovered that if I press down on two slides as I push them together, right in the center there is again kind of circular fringes. Okay, so that's this drawing over here. There's a derivation which I will put into the slide. It's fairly straightforward to follow just by looking at the geometry of these triangles. You can calculate how much this thickness of the film varies with now the position x. Okay, it's not just the angle of the alpha, but the radius of curvature. Basically, it's almost like a wedge, except that the angle is controlled by the radius of curvature. So from that, we can calculate the radius of curvature. So I'll just put a small extra video on that, and I'll also add the slide to the handout today so you can see how to derive that. But it's fairly straightforward. If you have any questions, you can ask me in the next class. Okay, that concludes sort of the the derivation. As I said, I'll add it, and that's it. So that brings us to the end for like Fizeau fringes, Newton's rings, which you've already seen. The last point, remember, is you can distinguish it from Heidinger because the fringe has the lowest order at the center. Again, just like Fizeau fringes, the lowest order is a dark fringe. I mean, at the center is a dark fringe, right? So at the very center, you should get a dark fringe. Whereas for the Fizeau fringes, you get a bright fringe because that's where the thickness is a maximum. The optical path length difference is a maximum. Okay, all right. So I'll stop there.